My name is Sandeep Gupta. I'm a product manager in Google.
And I'm Yannick Assogba, and I'm a software engineer on the TensorFlow.js team.
And we are here to talk to you today about machine learning and JavaScript. So the video that you just saw, this was our very first AI-inspired Google Doodle. And it was able to bring machine learning to life in a very fun and creative way to millions of users. And what users were able to do with this is that you were able to use a machine learning model directly running in the browser that was able to synthesize a Bach-style harmony. And what made this possible was this library called TensorFlow.js. So TensorFlow.js is an open source library for machine learning in JavaScript. It's part of the TensorFlow family of products, and it's built specifically to make it easier for JavaScript developers to build and use machine learning models within their JavaScript applications. You use this library in one of three ways. You can use one of the pre-existing pre-trained models that we provide and directly run them within your JavaScript applications. You can use one of the models that we have packaged for you, or you can take pretty much any TensorFlow model that you have and use a converter and run it with TensorFlow JavaScript. You can use a previously trained model and then retrain it with your own data to customize it. And this is often useful to solve the problem that's of interest to you. This is done using a technique called transfer learning. And then lastly, it's a full-featured JavaScript library that lets you write and author models directly with JavaScript. And so you can create a completely new model from scratch. Today in this talk, we will talk a lot about the first and the third one of these. For the retraining examples, there are a bunch of these on our website and in the code labs. And we encourage you to sort of take a look after the talk. The other part is that JavaScript is a very versatile language, and it works on a variety of platforms. So you can use TensorFlow.js on all of these platforms. We see a ton of use cases in the browser, and it has a lot of advantages because browser is super interactive. You have easy access to sensors such as webcam and microphone, which you can then bring into your machine learning models. And also, we use WebGL-based acceleration. So if you have a GPU in your system, you can take advantage of that and get really good performance. TensorFlow.js will also run server-side using Node.js. It runs on a variety of mobile platforms in iOS and Android using mobile web platforms. And also, it can run in desktop applications using Electron. And we'll see later in the talk more examples of this. So we launched TensorFlow.js 1 year back, last March. And then earlier this year at our Developer Summit, we released version 1.0. And we've been amazed to see really good adoption and usage by the community and some really good sort of popularity numbers. We are really, really excited to see more than 100 external contributors who are contributing to and making the library better. So for those of you who are in the audience or those of you listening, thank you very much from all of the TensorFlow.js team. So let's dive a little bit deeper into the library and see how it is used. Okay, I'm going to start with looking at some pre-trained models first. So I want to show you a few of these today. So we have packaged a variety or a collection of pre-trained models for use out of the box to solve some of the most common types of ML problems that you might encounter. These work with images. So for tasks such as image classification, detecting objects, segmenting objects, and finding boundaries of objects, recognizing human gesture and human pose from image or video data. We have a few audio models which work with speech commands to recognize spoken words. We have a couple of text models for analyzing, understanding, and classifying text. All of these models are packaged with very easy-to-use wrapped APIs for easy consumption in JavaScript applications. You can either NPM install them, or you can directly use them from our hosted scripts with nothing to install. So let's take a look at two examples. The first model I want to show you is an image-based model. It's called BodyPix. So this is a model that lets you take image data, and it finds whether there is a person in that image or not. And if there is a person, it will segment out the boundary of that person. So it will label each pixel as whether it belongs to the person or not. And you can also do body part segmentation, so it can further divide up the pixels that belong to a person into one of 24 body parts. So let's take a look at what the code looks like and how you would use a model like this. So you start by loading the library and by loading the model using the script tag from our hosted scripts. You choose an image file. You can load it from disk, or you could point to a webcam element to load it from the webcam. And once you have an image, then you create an instance of the BodyPix model, and you call its person segmentation method on the image that you have chosen. Because this runs asynchronously, you wait for the result, and we do that by using the await keyword. So once you get back the segmentation result, it returns an object, and this object has the width and the height of the image, and also a binary array of zeros and ones with the pixels where the person is found are labeled. And you see that in that image on the right. You could also use the body part segmentation method instead of the person segmentation method, in which case you would get the sub-body part classification. The model is also packaged with a set of utility functions for rendering. And here you see the example of the draw pixelated mask function, which produces this image on the right. OK, so this is how you could use one of these image-based models directly in your web application. The second model I want to show you is a speech commands model. So this is an audio model that will listen to microphone data and try to recognize some spoken words. So you can use this to build voice controls interfaces or to recognize words and for translation and other types of applications. So let me quickly switch to the demo laptop. So we have a small glitch application written which uses the speech commands model. And we are using a version of a pre-trained model which is trained on a vocabulary of just 4 simple words: up, down, left, and right. So when I click Start and I can speak these words, this application will display a matching emoji. So let's try it out. Left, up, left, down, down. OK, right, left, up. There we go. So we can go back to the screen. This actually points to what you would frequently encounter with machine learning models. There are a lot of other factors that you have to account for, things like background noise and just training data representing adequately the type of data that it will encounter in real life. So let's again take a look at what the code would look like. Again, you use the script tag similar to before to load the model and to load our library. And now we create an instance of this speech commands model, and we initialize it, or we use a version of the speech commands model that's trained for the specific vocabulary of interest. So in this case, it's this directional 4-word vocabulary. We have packaged this model with a couple of other vocabularies that you can use. And also, you can extend this model to your own vocabulary using transfer learning. And we have a code lab which shows how to do that. So once you have initiated the model, then we call its listen method, which starts listening to the microphone data. And then once it recognizes these words, then it returns a set of probabilities for the matching score for each of the spoken words in its set of labeled classes. And then once you've figured out what the spoken word is, then you can use that to display emojis, for example, in that particular example. OK. So I'm going to turn it over to Yannick, who will show you how to do training using this library.
Thanks, Sandeep. Hello. So Sandeep showed you one of the simplest ways to get started with machine learning with TensorFlow.js. And that's to take one of our pre-trained models, incorporate it into your app. And if you noticed, you won't even have to think about tensors. But there are situations where there won't be a model that works out of the box for your use case. And that's where training comes in. So TensorFlow.js has a full API to support training custom models right in JavaScript. So last year here at I/O, we showed a demo of training a game controller using webcam input, in this example, your face, to control this Pac-Man game. And this year, we're going to look a bit more closely at the training process, focusing on training in Node.js and what it looks like to bring your own data. Now, some of the advantages of training in Node.js include generally increased access to memory and storage, increased performance in certain situations, and importantly, being able to browse the internet while you wait for your model to train. In the browser, when you're training a model, you have to keep the tab focused, else many browsers will throttle performance on that tab. So it's quite handy that you're able to do something else. All right, so let's train a custom text classifier. And there are really two main things I'd like you to take away from this exercise. The first is generally how to work with text in TensorFlow.js, and the other is a general principle of using an existing building block to bootstrap your machine learning project. This is referred to as transfer learning, and it's really helpful when you're getting started with machine learning. And we'll see more about that in the example. But to step back a bit, what can you do with a text classifier? So there are classical examples such as sentiment analysis or spam detection. But you can also do things like log scrubbing, where you may look through your logs for maybe personal or private information that you don't want to keep and obfuscate it or remove it before you store it. But you can also do things like analyze product reviews or do document clustering. But today, we're going to build a component for a chatbot. And in particular, we're going to look at classifying user intents. So for example, given the sentence, will it rain in the next 30 minutes, we want the model to detect that that's a get weather intent. Or something like play the latest Bach album should be a play music intent. So any machine learning project needs data to learn from. And today, the data we're going to use comes from the SNPs AI NLU benchmark. And it's an open source data set that's available on GitHub. And for our first task, we're basically going to start with a spreadsheet. As you can see, it has the query sentences on one side and the intents on the other. However, one thing we need to do is convert this text into numbers so that we can feed it into our neural network, because neural networks don't really understand text natively. And that is where the universal sentence encoder comes in. It's a deep neural network created by Google that I like to think of as NLP in a box. It takes sentences and turns them into lists of numbers that encode the meaning and syntax of those sentences. And we'll take a look at an example. So let's think of this example. What is the weather in Cambridge, Massachusetts? The universal sentence encoder will take that sentence and turn it into an array of 512 numbers. And it will always be 512 numbers regardless of the length of the sentence, which is actually quite nice because it gives us a regular sort of structure to work with. And this is what the code looks like to create those numbers. So similar to what Sandeep showed earlier, we load our pre-trained model, the universal sentence encoder. We wait for its weights to finish loading. And then we call this model.embed with the sentences that we want to pass in. And this process of turning these sentences into numbers is often referred to as embedding in machine learning terminology. And you'll kind of hear that term a bit. So this is a bit of what that looks like. Wait for the result, and that's our set of 512 numbers. OK. Next is the intent. So we also have to convert these into numbers. So since these are categories, and we have a small number of them, we can use a scheme called one-hot encoding to turn a label into a small array that has a 1 in the position corresponding to that label. So in this example, we have our get weather intent. And notice the first element of the array is a 1, and the rest are zeros. In the corner, you'll see the other two intents we're using in this demo, the play music one and the add to playlist. And there's always just a single 1 in the array representing which category this represents. And here's the code to do that. And it is basically an index lookup into a list. So we call the method tf.onehot, given the index of the label we want to encode, as well as the total number of categories we have. So here, get weather and 3. And then it's going to return that compact array that is our numerical representation of the label. All right. So now we have our inputs, or often as referred to in machine learning, our x's, and our targets, which are also referred to as y's often. And now our goal is to take the 512 numbers representing the input and predict that smaller array that's 100 that represents that particular intent. And we're going to train a model to do that. So let's code up a model. So this is the entire code for the model. It's not too much code, but it does a lot of work. And as you spend time with this, it becomes more and more familiar. At the top, we see our embedding dims, 512, and num classes that represent the size of the input and the output of the model, respectively. So 512 numbers coming in, 3 numbers going out. The part that's highlighted is the entire model definition. And I won't dwell on this too long, but this is a common building block you'll see in neural networks, and it's known as a dense network. So we start with a sequential model, and this network just has one layer, and it's the one dense layer, and its job is to convert 512 numbers to 3 numbers. That's its entire job. The deep learning part will have been taken care of by the universal sentence encoder. Finally, we compile the model to get it ready for training. And here we pick an optimizer, which is an algorithm that's going to drive the weight updates during the training process, as well as a loss function to tell us how well we're doing. And here we're picking one that's commonly used for classification tasks. So on to the training loop. So model.fit is the function that actually runs the whole training process. And here we're calling it with a few parameters. X's are our input sentences. Y's are those targets from our training set. And then 2 extra parameters. Epochs is a fancy word that refers to the number of times you go through the data set before you're done training. And you can set that kind of to whatever you want. Validation split is a fraction between 0 and 1, and it indicates a portion of the data that we're going to set aside and not train with, but we can use it to see how well we're doing at making predictions. So before we look at the demo itself, let's take a quick look at what the code to deploy that trained model would look like in the browser. And let's just take a quick sample. So we'd first load the models in the metadata, but for now, I just want you to focus on the 3 lines in the middle. So the basic process is that we take the input query from the user. We're going to use the universal sentence encoder to embed it into that numerical representation. Then we're going to call our model with model.predict to get our final prediction. We're going to call the .array to get the values out, and we're going to use that to drive our UI. And in this case, our UI is going to look something like this. And it's about 150 lines of JavaScript and about 100 lines of CSS. So it's not terribly large. So let's get our hands into it. So if you just switch to the demo laptop, please. All right. So we're just going to sort of take a quick tour of the code. It's all available on GitHub. So here is that spreadsheet that we started with, our queries and our intents. And I've done a bunch of the pre-processing beforehand so that we don't have to wait for that to complete. So the first step was converting it to tensors. And it's just those long lists of 512 numbers. JSON isn't the most efficient format to store this, but it's quite readable. So you can actually just look at what a tensor is. It's just a long list of numbers. We also have some metadata for our model. So these are the 3 classes that we're going to train. And we have about 6,000 sentences that we're going to learn from. Our model itself looks pretty much like what we saw in the slides. There's no surprises there. And finally, our script that's going to run the training. Its main job, it takes a bunch of options, but its main job is to load the data and train the model. So it's going to do that with model.fit, as we saw earlier. We're going to wait for that to be complete. And then we're going to save that model to disk. So that's going to save a JSON file and a binary file. The JSON file contains the sort of structure of the network. The binary file contains the weights in an efficient format. Both of those are loadable in the browser. And that's our basic process. So let's see what that kind of looks like. So here, I'm going to run the training script for this model. So yarn train intent. It's going to load our script, and use TensorFlow and CPU, and we're off to the races. So each one of these lines that it prints is an epoch, and that's a trip through the entire data set of about 6,000 sentences. And you notice it goes pretty quickly. It typically finishes in about 20 seconds, and boom, 19.90 today. And we've trained a model. It's done. We can now load that in the browser and use that to make predictions. You can look at the file that's produced. It's a really small model file. So I'm going to start this demo app, which is here in our app folder. And it's just like a client-side JavaScript app. And this is really where all the machine learning happens, where we make our predictions. So this is going to copy the model that we just trained over into the folder for the client-side app and launch it in dev mode. Actually, I'm going to lift this a bit higher. And now we can try and make predictions. So we can ask it, like, what is the in Cambridge? Sweet. And it responds with a nice cloud for, like, it has detected a weather query. Or we can say, play the latest Bach album. And it's correctly classified that as a play music one. Or even things like, put those sick beats on my running list. Not that I run terribly often, but we get the right response back of add to playlist. But what happens when you give it something surprising? Like, get me a pizza. Well, it's just going to throw its hands up and shrug. And that's actually quite useful. You generally don't want your model to do things when it's not the right thing that it's been trained to do. And how we've set this up is that we set a threshold for confidence in classification. And so it should be pretty confident in one of these classes before it takes that action. And that's very useful to think of when you're building a machine learning-driven app. It's sometimes good to say, I don't know, or not this. So sweet. That's our classifier. Let's head back to the slides for a bit. Whew. All right, so we built our custom classifier. Yay. And in many instances, that might be all that you need. It may be the final step of your pipeline, or once you have the specific intent, you can apply some handwritten rules to extract information and do the rest of your processing. However, we can train models to do more than just whole sentence classification. So, given our original query, what is the weather in Cambridge, Massachusetts, we may want to know what's the location-related aspect of this sentence. And that's what we're going to look at next. So we can reformulate our problem a bit to this. So given a sentence, we want to tag each word in the sentence with a tag, like TOK for generic token, or LOC for location. We could have other tag types, but for now, we're just going to focus on these two and the weather queries. Like before, we need to convert our text into numbers. And like before, we're going to use the universal sentence encoder to do that. We're just going to give it one word at a time. So now each word becomes an array of 512 numbers. And in addition, we're going to add these special tokens at the end of our sentences. And that's the __ pad tokens. These will have two purposes. They'll let us know when the end of the sentence is, but more importantly, we're going to add enough of them so that all of our sentences are effectively the same length. And this will be useful for us because it gives us a nice rectangular matrix that we can use during training, and that's just way more efficient to train. So this is roughly what our input will look like. There'll be sort of enough pad tokens to make everything a given length. What about our targets? So now we want to predict something for each word. And we're going to use one-hot encoding again. Conveniently, we have three categories like before. So we have our TOK category, our LOC for location, and the special pad category that will tell us when we've reached the end of the sentence. And we see the one-hot encoding scheme just like before. So once we've done that for our inputs and our outputs, we now have them represented as sequences. So now each sentence is a sequence of those arrays of numbers. And we need an appropriate model to handle them. So you can use a dense network like before, though I'd advise maybe adding some capacity to that. But today we're going to look at a special kind of network known as a recurrent neural network, and in particular, a special kind of layer known as an LSTM that is geared towards handling sequences. So let's take a look at that. So here is our new model function. First, I want you to notice that the start and end of it is pretty similar to what we saw before. Embedding dims is still 512, and the number of classes is still 3. We still start with a sequential model, and the end of it is pretty similar. We're going to compile it with the same optimizer and the same loss function. So really, the meat of it is in the middle. So instead of starting with a dense layer, we're going to use an LSTM layer. And this is a special kind of layer that's It's designed to learn across sequences. And here, think of each sentence as a sequence. So we're going to configure it, set a maximum sequence length, and then after that, we're going to do one more special thing. We're going to take the LSTM layer and wrap it in a bidirectional layer to give us a bidirectional LSTM. And this is useful because it allows the model to learn context in both directions. So you can think of it as reading the sentence left to right, and then right to left, and trying to learn from that. Finally, we end with a dense layer, and this is very common in classification problems, to end with a dense layer that has your number of output classes, the num classes that you see in the slide. But because of the LSTM stuff we did previously, we do have to wrap it in this time-distributed layer that's going to unroll some of the sequence stuff that happened earlier. So that's our entire model definition again. Let's get our hands into it again. Let's see what that looks like. So I'm going to go back to the demo machine suite. Let me close that and head to the code. Again, I've pre-prepared the data so we can see what that looks like. Here's our input data. And it's just the sentences broken up into words with the tag for each word. And somewhere in there, there's some LOC ones. So that's our input. Another thing I've done is I've pre-embedded all of the words and just written them to a file. So we can just look that up instead of calling the universal sentence encoder each time. So with that pre-processing done, we can look at our model definition. And, oh, sorry, this is the tagger model. And if you look at this on GitHub, you'll see that it's a little more involved than what's in the slide. And that's because the example we've put up allows you to train 3 different kinds of models. You can train a one-directional LSTM, the bidirectional LSTM we're talking about today, or a dense network. And that's just to let you compare and see how they behave. But other than that, it's pretty much the same. Our training script is very similar. The data is a bit bigger, so there's a little bit more data management. So we call fit dataset this time, and then we save that to disk just like before. So that's the outline of our process, and we can run that. So I'm just going to yarn train tagger, and we'll see what that looks like. So we'll start it. And all of this training, by the way, is just using CPU. So you don't necessarily need a GPU to do any training, but it does speed things up. So we've started training. And probably the first thing you've noticed is that it's a lot slower than before. The data is much bigger this time. Each word is 512 numbers. And the model is more complex. So it will take more time to train. And I'd say on average, it takes somewhere between 10 and 20 minutes, depending on what options you pick. So we're not going to wait for the whole thing. To speed up the presentation, I did train a model last night. So we're just going to use that and look at a demo app that's designed to sort of show you the process. So I'm just going to start that, yarn tagger. So we copy our model over just like before and start up our front-end application. And this is a demo app just designed to give you a sense of what is the pipeline that inputs are going through. So we can now enter a query like, what is the weather in Cambridge, MA? So the first line is our input sentence that's been tokenized. The sort of grid thing is a representation of those 512 numbers from the universal sentence encoder. And then below that is our top category that comes out. And you can see the Cambridge, Massachusetts is nicely classified as being location related. One nice thing about these models, you can try somewhat more complex ones, like what is the weather in White River Junction, Vermont? And that's a place I have actually been to. And it does get it correct. We have this longer location-related sequence, and it's correctly tagged the tokens as belonging to that. You'll notice the confidence on the VT is a little lower. If we use the more traditional capitalization, so what is the weather in White River Junction VT? You'll notice that the classification score for VT, the abbreviation for Vermont, goes way up. But because we've used a bidirectional LSTM, you'll also notice that the words before that, their confidence scores go up because it's reading the context in both directions. So that can be super handy. Another thing that's important to realize is that it's not just memorizing place names. So if we try just typing in White River Junction, it's not going to detect that as locations, or even White River Junction VT. And that's because it's learned to find these in the context of these weather-related queries. That's the training data. So it's not just gone and memorized a bunch of location names, for example. So it's important to keep in mind, like it's really based on what you gave it to train. All right, and we can switch back to the slides now. Sweet, that worked. So yay, we've trained an intent classifier and a model that can extract information from that identified intent. Sweet. So is it time to ship this into production? I would caution against this. So you really should take care to first test that your model is robust to different situations and that it will match your users' expectations. Machine learning models are probabilistic and behave differently based on often subtle differences in the training data used. So it's super important to have a good test set, including some tricky cases, and just validate that with your users to make sure it matches those expectations. And Google has a number of great resources online on this topic, and I also recommend checking out the Designing Human-Centered AI Products talk by some of our colleagues in Google Pair later this afternoon at I/O. So now you've seen a bit of what the workflow looks like to train a model. You can check out the full code on GitHub. I've included a short link to it here, and it's part of our larger repository of examples. And next, I'm going to hand it back to Sandeep to talk about different ways that TensorFlow.js has been used. Thanks.
Thank you, Yannick. So we saw how the library can be used for using and training machine learning models. I want to just take a few minutes and quickly show you a variety of applications of what people are doing with TensorFlow.js. We saw earlier that it runs on a bunch of different platforms. So these examples will sort of span many of these. Creatability, this is a project that's being developed by the Creative Labs team in Google. And this consists of a set of experiments where they're exploring how to use AI and ML to make these creative tools more accessible. These run machine learning models in the browser. And in this particular case, you see a person controlling a keyboard with head gestures and head motion. They have some really cool examples, and I encourage you to check out the experiment sandbox, which is showing many of these, or on the website. Uber uses machine learning in a very significant way for a wide variety of problems at a very large scale. And Manifold is a browser-based application that Uber uses to visualize and debug their machine learning models and sort of data pipelines. So this application runs in the browser, and they're using TensorFlow.js for a lot of numerical computations that they want to use here. So for example, distance calculations and visualization, as well as clustering of data, et cetera. They were able to find that because of the WebGL acceleration, they could accelerate these computations more than 100x compared to just natively using JavaScript. Airbnb has an interesting use case where their trust team, when a user is trying to upload a profile picture to the Airbnb website, sometimes people accidentally use like a driver's license picture or a passport picture, which may end up containing personal sensitive information. So Airbnb runs a machine learning model directly on your client side in the browser or on device, so that if you were to choose a picture which may have some such sensitive information, it will alert you before you upload that picture and prevent you from doing that. On the server side, Clinic.js is a really nice example of an application that Nearform has built. This is a Node.js-based application which is used for profiling node jobs or node processes. And they're using TensorFlow.js to look for anomalies or spikes in CPU usage or memory consumption of these node applications. So it's a really nice example of server-side application of TensorFlow.js. In the desktop, TensorFlow.js can be used with Electron. And Magenta Studio is a set of plugins that has packaged a collection of machine learning models for music generation that use TensorFlow.js and for some very fun and creative music applications. I think Magenta has a talk later today that you might want to check out, and they also have some demos in the sandbox. We have the Ableton Live plugin for this in our sandbox that you can see. TensorFlow.js also runs on mobile platforms, on mobile web, both on iOS and Android. And recently, we have been working on adding support for the WeChat application. So WeChat is a very popular social media platform, messaging application, and it has a mini program environment which lets developers build these small JavaScript applications called mini programs and easily deploy and share them. So let's take a quick look at a prototype of what this could look like. So in this video, what you will see is a game, a Pac-Man game that's shared as a WeChat mini app, and it will let the user control this game using head motion from the phone's camera. So you see the WeChat application being launched here, and then one of my friends has shared this mini program via a link, and I just click on it, and I launch this game. And now this game is a little JavaScript program that's running within the WeChat environment. After I do a very quick calibration step by looking straight up at the phone, I'm ready to play this game. And so this Pac-Man game is loaded, and you will see in a moment my head motion is driving that little Pac-Man character. So really fun way of interacting with device. And the nice thing is that you can do a variety of things using webcams, using text, using speech, and have a very convenient way of sharing these applications without having to install anything. So we saw a bunch of examples. Just want to quickly show you that the community has been building some really interesting applications and use cases beyond all the examples that I've shown you so far. And for those of you in the audience who have been using TensorFlow.js, a big thank you. We have a collection of these examples that you can check out on our gallery page, which are extending TensorFlow.js and using it for things like reinforcement learning for that self-driving car example, or generative models, and a variety of other interesting applications. We also have a bunch of developers who are building add-on libraries as extensions on top of TensorFlow.js. And these are extending TensorFlow.js in very useful ways for libraries that let you track hand gestures, or facial movement and facial gestures, or also do more things like hyperparameter tuning of machine learning models, etc. So there are a bunch of these resources also available on our website. So in closing, I want to just point out a couple of resources to help you get started. There is this new textbook that is coming out. It's called Deep Learning with JavaScript, and it's written by our colleagues on the TensorFlow.js team. It's an excellent resource for learning about deep learning and machine learning, and all examples are written in JavaScript using TensorFlow.js. For our audience here and people listening, we have a really nice sort of an offer of a discount code, so that might find that useful. TensorFlow recently also launched a new Coursera course with deep learning AI to introduce TensorFlow and machine learning. And as part of this course, we will have a module on TensorFlow.js, which will be launching in a couple of weeks. So I just want to point out a few more useful links on our website for our models repo, for our gallery. And then also, we have an office hours session right here in Google I/O tomorrow. You can come by and ask your questions and meet the TensorFlow.js team. You can check out many more demos at our demo station in the AI/ML sandbox. And also, there are a few hands-on code labs that you can try interactively in the code labs area. So thank you so much for coming out here today, and have a great rest of the I/O.